Welcome back. We are switching topics now. Weak convergence is in the pocket for the moment. And we are going to switch towards two examples. The first example is going to take 2 or 3 weeks. It's about weak convergence in the real numbers or in RD. And the second example afterwards is about weak convergence on continuous functions, which we are going to need for the convergence of the random walks towards the Brownian motion in the very end of the lecture. So now we go back to measures on real numbers and on RD, and are going to discuss characteristic functions and the central limit theorem. This first lecture on this topic is for the time being the last lecture on abstract theory, where we go into general metric spaces. From the next lecture onwards, we're going to go back to real numbers and RD. Okay, so we need a little bit more on separating families. Recall, a family of functions is separating for a family of measures if the integrals of the measures against those functions determine the measures. So if you have two measures and integrals against these two measures are the same for all functions from that separating family, then the measures are the same. So this was obviously trivial for indicator functions because integrals are just measures. We proved it to be the case for bounded continuous functions and Lipschitz functions, but we still need this for the next lectures, for polynomials, exponential functions, so classes of functions that analytically are much easier because everything is much more explicit. In the end of the day, we are going to come back to questions of that form that we know from Stochastic 1, whether moment generating functions uniquely determine the distribution. So if the moment generating functions are the same, then the random variables x and y have the same distribution. We used this in Stochastic 1, but it was never proved. And now we want to go towards a proof of this. So we're going to talk about so-called characteristic functions much more than about moment generating functions. Characteristic functions are very similar, but they need complex exponentials. The big advantage about complex exponentials and their expectations compared to non-complex ones is this one is always bounded by 1. So this one is always defined, in contrast to moment generating functions, which are not always defined. So that's why we're going to talk about exponential functions here, which have complex elements. And we're going to talk about separating families, for which we're going to prove that exponential functions are going to be nice. Okay, so let's start to recall something about complex numbers. So reminder from analysis 1 and analysis 2, the complex numbers as a set is nothing but r squared, the real plane. The difference is we're not writing uv usually, but we are writing u plus iv. The reason is we're defining different operations on r squared to make it a field. A field is Körper. R squared is not a field, but with the right defined multiplication, it becomes a field, and then we call it the complex numbers. So recall some more definitions, properties, etc. from analysis 1 and 2. So the absolute value of a complex number is just the length of the vector. We have polar coordinate representations. So a vector is represented uniquely by the length and the angle. And this was written in this form. Multiplication can be either defined algebraically by giving a formula for this, or multiplication can be defined through polar coordinates, which make the interpretation simpler, because multiplication means take two vectors, multiply their length, and add their angles. So the product of these two elements might be, in this drawing, this element. Multiply the length, add the angles. Well, adding angles gives roughly this one, and that's supposed to be the product of the length. So that's multiplication, which makes C a field with the 0 element being the 0 vector and the 1 element being the 1, 0 vector. We call 0, 1 I. Comes apparent from that notation. So we have convex conjugation, where we just map this one to the one mirrored on the x-axis. We call this the real part, this the real part, this the imaginary part. What else do we need? We know we can write the real part in this form. So we take this vector, add the conjugate, and divide by 2. Well, this gives the real part. We can do the same with the imaginary part. Imaginary part is taking the vector, subtracting the conjugate, and taking a half, gives this one. Okay, so this is useful by simple operations in the field to get a formula for real in the imaginary part. So the exponential function can be defined in different ways. So one way is to define it as an analysis 1 in the real case as a power series. So we have defined multiplication and multiplication with scalars and sums, so we can define it. Convergence of series is defined in exactly the same way, since the complex numbers with this norm are normed space. So either we define it like this, or we use the Euler formula as a definition. So I think in analysis 1 or 2, we defined it this way and then proved the Euler formula. So what is Euler formula? So we can compute with the exponential function just as if we compute with real values. So here we have the multiplication formula for the exponential, and the exponential of v being real, has this Euler formula. Okay, what else do we need? So this is the exponential function. We can compute with the exponential function just as usual. We cannot draw it this way. We can only draw it this way for reals, but for the complex, the values are complex. So it should be a function from the plane to the plane. Important for us later for probability purposes, because this justifies that all expectations are well defined. The absolute value of exponential IV is 1. And the reason is just Euler formula. So this is the representation of the complex exponential, and checking the norm. So we need the squared of the cosinus plus the squared of the sinus. So we have these additivity formulas for cosine and sine. This gives 1. Analysis 1. So this has absolute value 1. And also we have formulas for cosine and sine, just using these definitions. Okay, so important, C with the absolute value is a Polish metric space. Well, it's a normed space which is compact, not compact, which is complete and separable. The separable set is Q squared. What else? Just as we discussed in stochastic ions for random vectors, F, a mapping from omega to C, can be interpreted as a vector. F is F1, F2. Well, usually we're not going to write F1, F2, but real part of F and imaginary part of F. And F is measurable if and only if both of them are measurable. Same with continuity. Okay, but for continuity stuff, we already discussed in analysis 2. Measurability is new. So if both of them are measurable, well, exactly in that case, F is measurable. So what else? Integrals. So this is new. And unfortunately, this gives quite a bit of a gap in the education at the University of Mannheim. think this, in terms of probability, this is more or less the only gap in our education. Funktionentheory is missing. So what are complex integrals and how do you compute complex integrals? This is Funktionentheory. So what we are going to need is the integral of f, if f is a mapping from some measurable space omega to c. In stochastic 1, the integral was only defined for mappings from omega to r. So here's a definition for mapping f from omega to c. We just define it to be the sum of the integral over the real part plus I times the integral over the imaginary part. So this is real valued, this is real valued, and since I put I in front, this is complex valued. So the integral of a complex valued function is complex valued. So of course we need to care about well-defined and existence. When we say it existed, both of them exist. So that's about it, what we need for the complex numbers. And for this lecture today, we're not going to talk about complex numbers again. We need to prove two theorems before, in the next lecture, we go back from abstract stuff and talk about complex integrals in order to discuss about these characteristic functions. Okay, so the last two theorems we are going to need. So we want to get rid of bounded continuous functions to determine measures. We only want to talk about polynomials or exponential functions, the reason being that we can compute expectations more easily. So we need two theorems, the so-called Weierstrass approximation theorem and a generalization called Stone-Weierstrass approximation theorem, which both say essentially polynomials are dense in continuous functions. So for Weierstrass, this is a statement, and for Stone-Weierstrass, there's a generalization for which this is the most important example, but there are going to be other important examples. Okay, so that's our target. We want to show, in the end of the day, that such expectations uniquely determine the random variable x. So this is a question about separating families. Separating families are families that uniquely determine measures through integrals, and these are integrals. Now, that's the integral e to the tx dp x of x. Okay, so functional analysis, Weierstrass approximation theorem. For those of you who attended function analysis, you probably know a proof, but I'm quite sure the proof you're going to see now is much cooler, because Weierstrass approximation theorem can be proved with the same techniques we used to prove the weak law of large numbers. So what's the statement of the theorem? The statement of the theorem, in an abstract way, is to say the polynomials are dense in the continuous functions from 0, 1 to r. Okay, without the abstract formulation, the statement is as follows. Take f from 0, 1 to r continuous. Okay, so we are really in analysis 1 setting. We have a function which is continuous from 0, 1 to r. Then there exists a sequence of polynomials which uniformly converges to f. So this is our function f. And now we have a sequence of polynomials which is getting uniformly closer and closer to f. Be careful. Your first thought might be, well, I can do Taylor. Let's take Taylor polynomials, and we know Taylor polynomials converge to the function, but only if the function is smooth. We can use Taylor if f is a C infinity function, but we're not assuming f is even once differentiable. F is allowed to be this, so Taylor wouldn't work. So this is not Taylor, it's more abstract or more general, because we can also do non-differentiable functions. So how do we prove this? So the amazing point is we're just writing down explicitly the polynomials, and the polynomials are expectations, which we can estimate with Chebyshev inequality and BNMA. Okay, sounds absolutely weird, but it's true. So the point is the following. We choose an IID sequence of Bernoulli random variables. Random variables only taking values 1 or 0, 1 with probability P. Then we take the sum. Sum looks like law of large numbers. We know convolution formula, Faltungsformel. The sum of these is binomial distributed with parameters n and parameters p. Okay, next. We know there's a minus p missing, sorry. We know how to estimate from the law of large numbers the probability that this sum divided by n minus p is larger than epsilon. Well, what is p in this case? P is the expectation of x1. Or, since it's a sum and they are IID, this is P is the expectation of Sn divided by n. So this is the probability of a random variable minus its expectation. Okay, then we have Chebyshev, the upper bound being the variance of this random variable. I pulled out 1 over n as 1 over n squared already. So the original Chebyshev, we have 1 over n here, but I can pull this out as 1 over n squared and then divide it by epsilon squared. That's Chebyshev. So now the point is, this I can compute. Okay, the variance of the sum is nothing but the sum of the variances, BNMA, since they're independent. And since they're identically distributed, it's the variance of each of them times n. So it's n times the variance of Bernoulli random variable. Check the computation if you forgot. The variance is p times 1 minus p divided by epsilon. Okay, so which is just canceling p times 1 minus p divided by n times epsilon. So this is what we're going to need in a moment. Okay, we are not at all close to Weierstrass approximation. And here comes the point why we are actually close to Weierstrass approximation. So let's do the following. Let's compute for our given function f, the expectation of f of this Sn divided by n. So this is actually just a random variable, x, which is binomially distributed. Sorry, x divided by n. So this is just expectation of a function of a Bernoulli. So what do we need to do? We need to take the sum over, take the function, plug in the value k. This is, in an abstract way, this is g of k multiplied by pk. The probability, the random variable takes the value k. So what is pk if I have a binomial random variable with parameters n and p? It's just this one. This is just binomial random variables. And this is just the function, which in this case is f of x divided by n, plug in x equal to k. So here's the point. This is a polynomial. So these are just powers. It's a polynomial in P. That's a polynomial. So if you multiply all this, you get polynomial factors. These are just some numbers. These are just some numbers. That's a polynomial of order n. And we call this Fn of P. In fact, this formula, which very naturally just comes out of probability, has a name. These ones here are called Bernstein polynomials. So this one, this polynomial, this function P, is a polynomial, it's called Bernstein polynomial. And these are just some other factors. In the polynomial, I have just some constants in front of the power terms. These are just some other terms. So all this is a polynomial. And what I'm just telling you for our given function f, we have a sequence Fn of polynomials. And the claim is this sequence does the job. So let's first think for a quick second why we have pointwise convergence. or we need uniform convergence, but I'm claiming pointwise convergence is easy. Well, we know Sn divided by n converges almost surely to the expectation of x1, which is p. So this one converges almost surely to p. Well, but if it converges almost surely, it always also converges in distribution. Okay, and f is continuous and bounded. It's on 0, 1, so it's automatically bounded. A continuous function on compact sets is bounded. So by weak convergence, I automatically know that this term here converges to expectation of f of p. It's slow. So, but since f of p is deterministic, this is f of p. So we have pointwise convergence for every fixed p. But that's not enough. We want uniform convergence. But convergence in distribution gives us pointwise. Okay, no trouble. We can also prove the uniform convergence. How do we do this? So what we need to do is we need to estimate uniformly in p from 0, 1 this difference. I need to show the supremum of this goes to 0. So let's estimate this. So the point is the following. We do two things. We use the estimate from above, this one here, and we use the continuity. And we do it as follows. So first recall that for some fixed epsilon, since f is uniformly continuous functions, it's just real functions. Continuous functions on compact intervals are uniformly integrable, so the choice of delta does not depend on epsilon. So since f is uniformly continuous, we have the following statement. For our fixed epsilon, there's a delta, so that if x minus x prime is smaller than delta, then f of x minus f of x prime, absolute value is smaller than epsilon. So we use this. Okay, so there's something else we can do. If we want to bound such a difference, the other extreme bound we always have for such a difference is we can bound these terms by, by it's smaller or equal to the absolute value of both. Well, that's a drastic estimate. And both of them are functions of f, but f is bounded. So both of them I can estimate with the maximum of f. But since I have it twice, I can do it twice. So I can always estimate the difference like this. So what we're doing now is the following. So if in a second we want to estimate our main term, we use this estimate. So we take the absolute value of the difference, multiply it with 1. 1 is not changing anything. Okay, so now the 1 I write as the indicator of some event plus the indicator of the event complement. And the event of our choice is going to be the event, the absolute value of the sum divided by n minus p is larger or equal to delta, or its complement, which is saying the indicator of n divided by n minus p is smaller than delta. So if Sn minus p is smaller than delta, then I'm in this setting. So if this is smaller than delta, then here this is x and this is x prime, then I know f of x minus f of x prime is smaller than epsilon. So on that event, this term here is smaller than epsilon. Okay, now that's what I'm doing. On the event, I estimate with epsilon, and on the other event, which is this one, so now that's the other indicator, I estimate the difference with 2 times the supremum of f. Okay, so this is just choosing this set and the complement. On the complement, I use this. On this set, I'm not doing anything. I just keep the indicator from here, but I estimate the absolute value by 2 times the supremum. So now we are almost at the end. So what do we want to prove? We want to prove uniform convergence of this one. So we want to show this goes to 0 independently of p. So let's rewrite it. So first, the main observation, fn of p is our expectation. That's definition of fn of p. So f of p is deterministic, so we can just say it's the same as the expectation of it. Nothing happens. So now we use linearity. So this is actually only one expectation of the difference. We use triangle inequality to put the absolute value inside. Here we have this. So now, with this one, we do what we have here. So we estimate the inside with epsilon plus this indicator. So now we have the expectation of two things. Use linearity. This is expectation of epsilon, which is a constant, so we can ignore the expectation. And the second term is the expectation of this term here. It's 2 times the maximum. We take it out, and we keep expectation of the indicator. So expectation of the indicator is the probability of the indicator set, which is this. Okay, so now what is this? Well, that looks good because we should have estimated this here, up here. So that's just our Chebyshev plus Bienname estimate. So the second term is, by the computation above, bounded by this one. So and here comes now the importance of the compact interval. We used it already for the uniform continuity. Here we use it again. Well, that term, all these p's, well, they're between 0 and 1. So that term here is more or equal to 1. So in total, what do we have? The supremum norm of Fn, our particular choice of polynomials, which is the supremum, is more or equal to epsilon plus 2 times supremum of F. So now this is of course wrong. It's the supremum of P missing, but I can replace the supremum of P by 1. So this is 1 times n divided by epsilon. And this goes to epsilon as n goes to infinity. And since epsilon was arbitrary, we proved our supremum norm goes to 0. That's it. Wonderful. I'm pretty sure the proof from function analysis was not half as nice as this one. So keep this in mind. Every continuous function can be approximated uniformly by polynomials, or in other words, C01 is separable normed space, separable metric space, and the separable set are the polynomials. Good. So now we want to generalize it. So this is a statement essentially from analysis 1. It's about functions from R to R. So there are several generalizations, and we're going to prove a theorem of Stone. So Stone generalized Weierstrass theorem, where the generalization is in 2 directions. One direction is to generalize the interval 0, 1. Just for fun, I'm writing the theorem in a super general way, but we are only going to need it for Rn on compact sets. Never mind. I just want to show you where these Hausdorff things that you might have seen somewhere already are useful, but we don't need this at all. You do think of Rd. So the generalization is from the interval to any compact set in Rd. And the second point in the generalization is Stone removed the polynomials. You don't need polynomials. What you need is a property of polynomials, that they are closed essentially under multiplication and addition, and they have constant functions in there. So this is what we are going to do now. And we first need the generalized notion of polynomials, which is called an algebra of functions. So here's the definition. Take a metric space. We don't need the metric space, actually. We need a topological space. I changed it in the notes. We don't need metric space. So take some nice space, then choose the field R or C, and then we're studying functions from E to either R or C, which we just abbreviate with K. A subset of the bounded and continuous functions, which we call C, is called an algebra if constants are in C, the constant 1 function actually, C is closed under multiplication and addition, and C is closed under scalar multiplication. So 1 and C together implies that all constant functions are in C. Now the 1 function, but I'm allowed to multiply the 1 function with all scalars. So that's called an algebra. And polynomials are an example. We need to be a little bit careful. The statement I made is not quite true. We want a subset of bounded continuous functions. Polynomials are not bounded. But we are only going to talk about compact E in the theorem, and on compacts, of course, polynomials are bounded. So that's an algebra of functions. Now we say that set C separates points of E if for all pairs of points we find a function in C so that f, or let's call the function f, so that f of x is not equal to f of y. Okay, so we are able to say that 2 points are not the same only by studying values of the functions of these sets. So as an example, only the constant functions are not separating points of E, because for all points and all functions, the values are just the same. So I cannot take only constant functions. Polynomials, of course, the usual polynomials you know from an analysis, are separating functions. You find, or you just take, well, you need to be careful. If I want to separate these points, I better don't take this polynomial where the points are the same, but I can take this polynomial. So polynomials separate points. So that's separating functions. And also an extra remark, I don't want to write this in all the theorems because the theorems are already messy enough. Whenever K is C, we assume that the function class is also closed under complex conjugation. So if f is in there, then the function f bar, which we obtain by pointwise conjugating every f, so f bar of x is just f of x bar. So this should also be in the class. So we are always going to assume this. So most important example, if K is C, we take the polynomial, the real polynomials. Okay, so I'm going to prove the Stone-Weierstrass theorem for compact Hausdorff space. Okay, as I said, we don't need metric space, we need some topological spaces. So what is a Hausdorff space? A Hausdorff space is a space in which the topology separates points. So if you have 2 points, then there are open sets containing these points, so they are neighborhoods, and the open sets are disjoint. So that's how open sets can separate points. And well, if you can do this for all points, then this is called a Hausdorff space. Not every topological space is Hausdorff, but everything you have in mind is Hausdorff. So most importantly, here's an example of a metric space. So if you have 2 points which are not the same in the metric space, then you know by the definition of a metric that the distance of x and y is strictly positive, say epsilon. Well, and then you take 2 balls of radii epsilon over 3, say. And then triangle inequality shows you these 2 are disjoint. So all metric spaces are Hausdorff. So that's why you can completely ignore what I'm saying, but the proof I'm writing down is not a single word longer, stating it in the general form. That's why I just, for didactic reasons, I just decided to formulate it in this general way, just for you to see very clearly what the proof needs. The proof needs nothing about the real number. It doesn't need anything about RD. It doesn't need anything of a metric space. What it needs is open sets that separate points. Okay, but please feel free to think of a metric space. Also feel free to think of RD. So here's a statement. So let E be a Hausdorff space. It must be compact. and K is either R or C. And if we have C, then we want the closeness under complex conjugation. Now let C be an algebra of functions that separates points as in the definition. Then C is automatically dense in the continuous bounded functions. Or I could also reformulate it as I did in here. I could say for every f bounded and continuous, there's a sequence of polynomials that converges weakly to f. Okay, that's a statement. Okay, so keep in mind, first we generalized the function, the spaces. We're not on the interval 0, 1, which we really needed for the probabilistic proof, because these were the parameters for the Bernoullis. Now we have some compact Hausdorff space. And second, we don't assume anything about the function classes except it's an algebra. No polynomials needed, but we keep polynomials in mind. And it's also important to note, in the applications next week for probability, we're not going to take polynomials. We really need algebras. So, proof. So that's the only tedious proof today. And after this proof, we are almost at the end. So the first step is the following. The first step is to prove that an algebra is also closed under taking maxima and minima. Actually, the statement is not quite correct. Maxima and minima of two functions from C are not necessarily in C, but they are in the closure of C. So the closure of C is going to be closed under maxima and minima. So that's what we're going to need in the construction. We're going to need closure under taking maxima and minima, but not in C. In C bar is enough. So that's what we are going to prove. And the reason is just as follows. The reason is the equality here. Maxima and minima you can write in this way. I think we did this in analysis 1 at some point. So we can write the maximum as a half of the sum of f plus g and the absolute value of the difference. So let's just quickly check why. So if the maximum of these two is f, so f is larger than g, then the absolute value can be omitted. F minus g is positive if f is larger than g. So skip this. Now cancel the g. You have 2 times f, divide by a half, gives f. So the same, if g is larger than f, this guy is negative, then you get rid of the absolute value by taking minus of that guy. So you have f minus f cancelled, so you have g minus g is 2g, 2 cancels a half gives g in total. So this is just trivially true. You just need to know it. So if I want to say something about max and something about min, I need to say something about absolute values. So we know f plus g is in C because C is closed for addition. If this guy is in C, then also the sum is in C. And since multiplying constants remains in C, I'm in C. Okay, so the statement would be true in C if the absolute value would be closed in C, but that's not true. But it's true in the closure. So if I take 2 functions in G, then this one as a difference is in C, then this one is in C, and we are going to show that the absolute value of a function in C is in C bar. And this is up here. So this is a trick. The trick uses Weierstrass approximation. So the trick is to write the absolute value of f in this way. So what's going to happen here? We are going to take a sequence Pn that converges uniformly to the square root on the interval 0, 1. So on the interval 0, 1, the square root is a bounded continuous function. So by Weierstrass theorem we proved before, we can approximate this by polynomials. And the polynomials uniformly converge to the square root. Let's call these polynomials Pn. So Pn pointwise converge to the square root. And they're polynomials. Okay, so this guy here, the limit of this one is the square root of the inside. So the square root of the inside gives the square root of f squared gives f divided supremum squared square root. This is supremum. Here is supremum. We cancel this one. We cancel this one. We get f. Okay, so that statement is clear. Okay, and it has nothing to do with anything. It only says that Pn of x converges to a square root of x, and we take this x. So all we need is 0, 1. This one must be in 0, 1. But of course, if I divide the function by the maximum of the function, and this one is also non-negative because of the squared, and the maximum also squared, then this is between 0 and 1. The maximum is, of course, larger or equal to f. So this is in 0, 1. This is a polynomial with values in 0, 1. These are, what is this? This is our function f, which is in C. Multiplication remains in C because it's an algebra, so this is in C. Multiplying with something in here that's a constant remains in C, so all this is in C. Polynomials are just sums and multiplications, so all this is in C. So all we see here is this is a limit of objects in C. This is a function in C. And multiplying, I can put the constant inside if I like. Multiplying with a constant remains in C. So bar f is a limit of functions in C. And the convergence is uniform because Pn converges uniformly to the square root. So this is in C bar. And that's it. So the absolute value of f is in C bar. So from all this stuff, this is in C, this is in C, this is in C bar, then this is in C bar. Okay, that's the first step. First step, keep it short, is just our closure of the algebra is closed for maxima and minima. So now from this, we're going to construct our approximation. So remember, we have a compact space. And in that compact space, the aim is to approximate our continuous function by a sequence in C. So we want to write our given function f as a limit of elements from C and the limit in uniform convergence. So the compactness is used as follows. Since I have a compact space, I can cover the compact space by finitely many open sets. Finitely many. So why can I do this in a compact space? Well, of course, I can take any open set around any point. So I can write E as the union over all x in E and open sets around x. Okay, for all point, I take an open set around this. And since x is in that open set, and I do this for all x, E is covered by those. Okay, but E is compact. So finitely many are enough. Okay, so this is the same as OX1, some x1, I don't know which ones, union and so on. So I can cover the space with open sets. And what I'm going to do is, for every open set of that space, it's mostly open intervals here in that picture. On every open set, I'm going to construct such a function, which is doing it. And then we are going to take the maximum over all these functions, and that's going to do the job. So this is the direction of the proof. So let's proceed formally. We have a fixed function f that we want to approximate. And in the first step, we fix x. X is fixed, and we fix epsilon. So now the claim is, we can construct a function gx in C bar. So gx is a limit of functions in C uniformly with the following two properties. for the fixed value x, our new function takes the value of the function f. Okay? And on top, in some, no, we don't want this, sorry. So we do this, and then additionally, we move our function f from epsilon inside, and we claim the function is smaller. So it's a function which is smaller than the function shifted by epsilon above, and at the point x, it's the same. So we want to construct a function like this, and then we proceed once we have this function. Okay, the point is we can just write down such a function in the following way. So here we need this separating property. So our family of functions C, by assumption, separates points. So let's take some z, which is not x. So because C separates, there's a function so that the function at the value z and the function at the value x is different. Without loss of generality, we can say the function at x is equal to 0. So if it's not 0, then we just subtract that value from that function. We just shift it down. But if x and z had different values before, well, then they also have different values after the shifting. So we have such a function hz. And now we define this function. We just write this down. So we know hz of z is non-zero, so we can divide by this. And we define h as f plus f of z minus f of x divided by this constant times hz of y. So why do we do this? Well, we do this because there are only operations which keep h in C. So f was in C. So this is just a constant function. Constant function is in C. Difference is in C. Multiplication with a constant is in C. H is in C. Yeah, this was the assumption. Multiplications are in C. So that guy is in C. Okay. So and now what? Now let's consider that function. So what do we know for that function? So just plugging in values. What happens if I plug in x? So if I plug in x, then I have f of, let's see. If I take x for y. Oh, yes. Here. If I take x, then this guy is 0. Because of this. So that term is 0, so I get f of x. Okay, that's fine. So if I plug in z, then I have f of z minus f of z, so this is 0. So what happens is that term, the second summand is 0, so hz of z is f of z. Okay, so these two properties hold. So now, what does it mean? So this means that this function, let's take this picture, suppose this is z, then we know we have some function which takes the value, the value of the function f in z, and it takes the function of f in x. Well, that's all we know. It's not saying anything else. So we can do this for all values. So we can also do it here. So we have a function that takes the value of f in this point z, it takes a value in x, and we don't know anything else. Okay, not so clear what we can do with it so far. So everything we have so far is continuous. So now we do something that we used in analysis already. If I have a function or two continuous functions, and they have the same value at some point, then there's a neighborhood so that one function is smaller than the other function plus epsilon. Okay, I think we did this with 0 actually. So suppose you have a continuous function by taking the difference, which is 0. Which is 0. So then there's a neighborhood, so that on the neighborhood, the function is between minus epsilon and epsilon. So that's a continuity. So we know for our function hz, there's a neighborhood of z, so that hz is smaller than f plus epsilon on that neighborhood. So let's take this value z here. So we have our function, which takes the value f of z here and f of z here. But now we say there's a neighborhood so that the function is smaller than the graph of f plus epsilon on that neighborhood. Okay? Well, we can do this. So not clear what this is useful. And now you see why this is useful. So for every point, we have these neighborhoods. For every point, we have these functions. And now these functions for every point are such that we know on that neighborhood, they are smaller than f plus epsilon. This one, and also this one, and also this one. These functions, they are all smaller than f plus epsilon on the neighborhoods. So now, we discussed at the very beginning, since our space is compact, we can cover the entire space with finitely many compact sets. So what we do is, we take finitely many of these points so that their neighborhoods on which the functions hz are smaller than f plus epsilon cover the entire space E. And here's a trick. Now we define the function gx to be the minimum of all those. So the minimum is good because the minimum is smaller or equal to all of them. So if on that interval, I know the function is smaller than f plus epsilon, then, and this is true for all of them, the minimum of all these functions satisfies on each of these neighborhoods that the minimum is smaller than f plus epsilon. So this function satisfies that property. Additionally, that function also satisfies gf of x is equal to f of x. Why? Well, because all these functions had the strange construction that they were equal to f at that point z, but also at the point x. So all of them are equal to f of x at the point x. So at x, all of these functions that I have involved, they all take the value f of x. So the minimum also does it. So this is a function that satisfies these two properties. And now we use the first step to say this is in C bar. Because it's a minimum. Well, we proved the minimum of two functions is in C bar, but by induction, of course, the minimum of finitely many is in C bar. So what we justified is we have such a function. So this is now a function with the property. If I have my function f, I enlarge the function f by epsilon, then it's a continuous function, which in x is f of x, and away from this is smaller than f plus epsilon. That's all we need. So now the trick is, we use these functions to do the same argument downwards. So we have all these functions gx, which are smaller than f plus epsilon. And with each of these functions, we are going to do the same argument as before to construct a new function, which is also bounded from below. So this is done as follows. Okay, how do we do this? So we have our function f, and now we have all these functions gx. We have constructed a function gx for any x. They're continuous. And by construction, we know f of x is equal to gx of x. So since they're continuous and we have that property, we know this function is also, here's now a value x, here's f, here's my function gx, which in x is the same. So now with the same argument as before, since they are the same in x, there's some neighborhood of x, so that this function is also larger than f minus epsilon. Okay, so now we have again the same argument. From all these functions gx over all x, And all these neighborhoods Vx, we only need finitely many to cover E. So now we do with the same. We have finitely many of these, let's draw it like circles. It's easier to understand the picture. So we have finitely many of those. So for each of them, we have our functions, which are smaller than f plus epsilon. All of them are smaller than f plus epsilon. And on all these intervals, they are larger than f minus epsilon. So we do the same as before. From all these functions, we take the maximum. Not the minimum, now the maximum. Again, the maximum stays in C bar. So that's a function, G in C bar, so that G is trapped between f plus epsilon and f minus epsilon. Or in other words, the supremum norm of the difference is smaller than epsilon. Since epsilon is arbitrary, or we can, if you like, you take a sequence 1 over n, which gives you a sequence Gn. So we found a sequence Gn that converges uniformly to f, or in other words, the closure of C bar is C bar, CB. It should formally be the closure of that set C bar, but the closure of the closure is the closure. So that's a proof. In the case of the real numbers. So now a simple trick that we need for the complex numbers. So now suppose we have functions which are formed in algebra. So all these multiplications and additions stay in that family of functions. But now the values are in C. Well, all this before here were real arguments. We had said f plus epsilon, smaller this, there's an ordering. All this were real valued arguments. So now we need to push the real valued arguments to the complex case. Okay, so we take that algebra C. So now we recall these formulas that we proved by drawing a little bit earlier. The real part of f and the imaginary part of f, I can write as these sums. Now, very important, we assumed that for complex functions, that algebra of functions is closed under complex conjugation. So this is in C, this is in C, the sum is in C, dividing by 2 is in C, this is in C. So real part, same for imaginary part, are both in C. So now we define the sets of imaginary and real parts of functions in C. So by this argument, they are subsets of C again. And in fact, they again form algebras. Well, you just check, you take the sum of these two. The sum of the real parts is the real part of the sum, but the sum is closed and the real part is closed, so it's again in there. So these are both algebras again, but now they are real functions. They take only real values. So there's one simple, no, not so simple, one tricky point that you need to keep in mind. So they are algebras. So we would like to apply the first part, say they, these ones separate. But there is, there's one tiny little point. We had that assumption, or not, they separate, they're dense. Sorry, what I just said. So we have the assumption it's an algebra, and we need that algebra separates points. Here it's written here in the assumption. So if I want to apply the first part of the theorem, I need that these two separate points. So why is this true? So if I have 2 points, x and y, and I know in C there's a complex function that separates points, why do I also know the real part separates points? It's not so obvious on first sight. So why? So suppose I have these 2 points, or I have 2 points, and the values f of x and f of y are both here or here. So they have the same real part. So if f separates 2 points, not necessarily the real part separates in the same way. Same with the imaginary part. If this is f of x, this is f of y, well then imaginary part of x, f of x and imaginary part of f of y are the same. Well, that doesn't work. Well, essentially the trick is just the following. If you have a function f that separates 2 points, then you can pull them around by taking a different function f. So if f gave you this, for instance, then this is the values of f, but then you multiply this by something else. You multiply this by some other point. And then what you do is you rotate them. So if they were like this before, then for a function f bar, they are like this. But f bar is still in C. Or it's not, let's call it f tilde. That's still in C. So and if you rotated these points, and now you take a real and imaginary part, now they are different. Okay, same idea for imaginary part. If you have 2 which are here, these are the values of f. So you multiply f by some appropriate constant. So you rotate these points, and after rotation, they are not on the same x transformation. So now the imaginary parts are different. So the same statement is C1 and C2 also separate points. So if both of them separate points and they are algebras, then their closure is continuous real functions. So, but now this goes back to analysis 2 again, because continuity of functions only refers to the norm, but not to the multiplication operations in the complex numbers. Convergence in the complex numbers is convergence in both coordinates separately. So the continuous functions are just the sum of continuous functions in R with values in R2 plus I times continuous functions with values in R again. So if these two in the closure give the continuous functions, then we know that C in the closure also gives the continuous functions. That's it. So keep in mind, we didn't do much today. We only proved polynomials are dense in continuous bounded functions on the unit interval. And more generally, function algebras, which are sets of functions essentially with the same properties as polynomials, they are also closed in the continuous bounded functions on some compact Hausdorff space. So on, say, a compact box in R squared. So we finished the lecture with a corollary. I wanted to finish here already because the last lectures were long, but I want to finish with this corollary so that next week we can really start with discussing real numbers, and this is the last abstract theorem or corollary. It follows directly from this. So it's about separating classes of functions or families of functions for measures. The statement is, same setting as before, let E be something compact. And C, as before, a family of, or a little bit less, a family which is only closed under multiplication. Yes, we only need closed under multiplication, and it contains 1, so constant functions. Then C is separating for M1. So we don't need the algebra. So we only need that separating family, which is closed under multiplication and contains 1. With sums, we see in a second why they can follow. Okay, claim is this separates the probability measures. So if we know that all integrals against 2 different probability measures are the same for these functions, then the measures are the same. So proof is very short. So we assume that for 2 probability measures, the integrals are the same for all functions in C. And we need to show mu1 is equal to mu2. So here's a trick why we have this statement which does not involve an algebra. You could write an algebra, but you can omit it because of this. So we define C prime now to be the algebra of all finite linear combinations from these C's. So these are all linear combinations. And linear combinations plus linear combinations are linear combinations. Now that's why this is an algebra. So by linearity of the integral, also these are the same. So if they are the same, and I take sums of two functions g, of course, also the integrals of two functions g are the same. Linearity of the integral. So if I'm only asking for equality of the integrals for the functions g, that I automatically get it in that algebra generated by C by just taking all finite linear combinations. So now the point is the following. All these functions g by Stone-Weierstrass are dense in F. So if I take any function f which is bounded and continuous, I can approximate the integral of f by integrals in g. I do it for mu2, 1, I do it for mu2, and then I take the limit. And now I have to write this down formally. So take f and cb, then we know we can approximate f uniformly by functions in that algebra. So take some function g, which has uniform difference at most epsilon. Do this by Stone-Weierstrass. So now we want to show this integral is small. We show this is smaller than epsilon, and since I can do this for all epsilon, I know the integrals are the same. So I do triangle inequality twice. So this difference is estimated from above by this minus this. Now I have to add this for triangle, minus this, and have to add this. So it's twice triangle inequality, getting in the game these four terms. So now let's look at each of them separately. That guy is 0. G is in C prime. But we know for C prime functions, the integrals are the same. Okay, can get rid of this one. So what is this? That's the same as the integral of f minus g d mu 1. And if I like, I also make it larger by taking the absolute value inside. Okay, so now I use monotonicity by taking inside the supremum of all of them. Now the supremum is larger or equal pointwise than all points. So now this is a constant I can pull out. And what remains is the absolute, the supremum norm times 1 because it's a probability measure. Or actually we see here we don't need probability measures. We can take finite measures, if you like, then there's a constant. So the same happens here. I do exactly the same. F minus g is just g minus f. So it gives exactly the same bound. So we have the upper bound. This is 1, 2 times f minus g, but this was supposed to be smaller than epsilon. So this guy is smaller or equal to 2 epsilon. Since epsilon was arbitrary, I find this is 0, so that integral is the same. So what did we prove? We proved the integrals are the same for all continuous bounded functions, but we already proved 2 lectures ago that continuous bounded functions are also separating. So if these integrals are the same for all continuous bounded, keep in mind this trick, then the measures are the same. Okay, so where are we? We know indicators are separating. Then we proved Lipschitz or continuous functions are separating for measures by approximating indicators. And now we know that also function algebras are separating by approximating these guys, which again approximate these guys. So this is what we're going to need in order to prove that next time characteristic functions determine the law, and that's what we're going to need to prove the central limit theorem.